Hey everybody, it's good to see you. I'm Jane Woodward. We're going to talk about fossil fuels. When we say fossil fuels, what are the 3 or 4 things we're talking about? Coal, gas, oil, and also natural gas liquids, but mainly coal, gas, and oil are the things I'm hoping you think about. When you think about the origin of all of those, what do they all come from fundamentally? Single-cell microorganisms. Yep. So all of it is chemical energy, right? That took tens and millions of years, tens to hundreds of millions of years to make, and we burn it like that, right? Talk about something that is not sustainable. So when we think about oil, gas, and coal, certainly oil and gas, one of the things you're going to hear later on is we tend to think of those industries as having an upstream, which is how you get it out of the ground, a midstream, which is how you refine it and move it around, and a downstream, which is the markets for those things. And so that's common to fossil fuels, less so for some other things we'll talk about. I think who knows who the largest producer and consumer of oil is in the world? Largest producer and consumer is China. So we like to ask big questions in this class. So, what's the impact of economic and technological changes? I mean, they're huge, and we're going to talk about them. In what ways do fossil fuels impact the environment and society? Huge. We're going to talk about them. And I like to break thinking about the impacts in terms of the poop you and my kids have inherited from the past. What are we doing today? And how can we impact the future in terms of what our patterns of energy use are, certainly with the fossil fuels. So let's dig into the content. And there are a bunch of key points here. So let's talk a little bit about some of these, not a lot. So hopefully everybody watched the video with its own dedicated slide deck really on the history of fossil fuels. Talked about the steam engine, talked about the automobile, going from carriages, how New York City changed in like 10 years from having a major environmental crisis around horse poop in the city to all of a sudden we have the internal combustion engine and we have cars, which is part of what drove that interesting change. So we're in a world where when I took this class 42 years ago, everybody was convinced we were going to run out of oil. Now we're in a world where the peak oil is not going to be driven by supply of oil. It's going to be driven by demand for oil. So that shows you what can happen in 40 years is a really tectonic shift in terms of how we think about supply and demand and what drives markets. We've talked about, all these facts here I think you already know. So rather than belaboring them, I think it's time to jump in. Chemical energy is key. Sedimentary rocks are key. And we're going to talk about the resources. So these are just all key ideas that we hope by the time you prepared for this lecture and you jump into it with me, that you have a stronger sense of. So, and I think towards the bottom where we talk about externalities, the externalities of fossil fuels are really significant. And I think most of you knew that, and it's part of the reason you're taking this class. But there's the land use impacts, there's air, there's water, and there's solid waste. And when we talk about air, we mean the Earth's atmosphere up at the high level that's causing global warming, but the air pollution issues that are closer to the ground as well. So one of the things that dates me, remember I told you I took this class 42 years ago and I'm only 39 years old, is the fact that when I took this class, honestly, we thought oil came from dinosaurs. And biochemistry came along and we were able to fingerprint source rocks that have kerogen in them. The origin of that is single-cell microorganisms like you saw in the video, and realized, it doesn't come from dinosaurs. It comes from dead microorganisms. So one of the reasons, so Sinclair Oil, which this is their logo, and if any of you are from Montana, Utah, or Idaho, there's a lot of Sinclair gas stations, and the logo is Dino the dinosaur. There are still changes in terms of how we perceive the world. This is like going from the world is flat to the world is round in terms of how we explore for oil and gas, how we understand it. And so I like to show this as an example to show you that in the course of 40 years, again, we can shift in terms of our understanding of where resources come from. So we could have a radical shift in where lithium comes from, for instance, which is relevant to the EV revolution. I don't want you to narrow your thinking about this example to thinking about fossil fuels. And so the innovation that you're all part of and that you're learning about here at Stanford is I just really want to encourage everybody to be prepared for the fact that just because the status quo is a certain idea, that doesn't mean it's necessarily the truth. And so it was kind of exciting to me to have this change take place. And ironically, I took a class on hydrocarbon source rock geochemistry as a master's student as this knowledge explosion was happening. And then I went to work for ARCO, and ARCO had me teach about 2,000 earth scientists what I learned at Stanford because they all needed to learn the new science. So I basically took my course and went to ARCO's lab and shared this knowledge and information with people. So maybe some of you will have the opportunity to train existing workforces that you go join on things you learned here at Stanford, because the rate of innovation of our understanding of things is actually pretty high right now. So again, you're going to say, Jane, we already discussed this, but key ideas about these three things, and you could add natural gas liquids to the list here, is these are depletable or stock or mineable resources. They occur in sedimentary rocks. They come from organic material that fundamentally was formed, it's ancient biomass. And we're going to talk a little bit more about the situations under which that biomass gets stored and subjected to time, temperature, and pressure. And the main way we harness fossil fuels is we burn them. So the relevance of fossil fuels is, from an energy perspective, if you look across the top in world and US energy use, it's about 80% of the story. So we have a lot of decarbonizing to achieve to get where we want to go in a world where the overall appetite for energy is still growing. So we're all interested in the sustainability of the planet. We're all interested in just transition, and that everybody have access to energy, and that the impacts of cold beers, hot showers, manufacturing, all the things we care about in terms of energy, comfortable rooms, the ability to charge our electronics. We care about all that. How do we move from where we are now? And you see the electric sector, very rich in coal globally. The role of coal in the United States has dropped dramatically due to our adoption of wind, solar, and natural gas. And as much as natural gas has challenges because it's a potent greenhouse gas, the flexibility of being able to dispatch natural gas on the grid almost instantaneously, not the way a battery can, but within minutes, allows, the role of natural gas has actually helped enable renewables in the US remarkably, because the wind doesn't blow all the time and the sun doesn't shine all the time. And so whenever renewables are not available, in a lot of places on the grid, natural gas has been the backup and has helped not completely kill coal, but greatly reduce the role of coal, which even 10 years ago, coal dominated electricity in the United States. So this is looking at that same information over time globally and showing you, there are people that argue, in California and various, we're banning the internal combustion engine in phasing it out in California. We're regulating county or state counties and cities are banning gas stoves and doing things like that. And a lot of people, when they see this graph, they say, well, nothing we're doing really matters. What really matters is all that coal in China. But this is giving you a sense that really just in the case of, since I took this class in 1980, over the last 42 years, how dramatic the growth in the role of fossil fuels has been globally, and which countries really matter in that mix. So this is back to, I call it I don't know if you guys even know what a crock pot is, but when I was growing up, before they had rice cookers, they had something called crock pots that you would slow cook and make soups and chili and stew and things like that. And so to me, the idea of a crock pot is something you cook over a long period of time. And so the idea of this slide is to highlight the fact that there's basically a similar broad recipe for the formation of oil, gas, and coal, which is you need lots of time, lots of temperature, lots of pressure. And then the organic material you start with is a little different in the different scenarios. And we're going to talk about plate tectonics here in a moment, which is you have organic material, and in the videos you guys watched, it showed sediment burying that. So you've got to bury the deeply organic rich rock that is, or sediment that is going to be your source material for oil, gas, or coal. You have to bury it deeply to subject it to enough pressure and temperature to have the metamorphosis take place that it will turn into these fossil fuels. So without elaborating too much on this slide, which is relatively self-explanatory, the idea, though, is that Coal generally is woody, peaty, planty material. Think of the Mississippi Delta or bayous or swamps. That's the kind of material, the kind of organic material people associate with coal. And oil is more major anoxic events in oceans or lakes that are rich in microorganisms. And there is an anoxic event where all that organic material dies off and settles onto the lake bed or ocean bed, and then is buried and subjected to time, temperature, and pressure. So for the purposes of this class, it's more that we're interested in you understanding the broad ideas about this. So what comes out of the crock pot chemically is the prince of hydrocarbons, which is so natural gas used to be the booby prize because it's a gas and it has a very low energy density, but it became the prince of hydrocarbons because it's so simple. And it's easiest to combust with the least impact other than the fact methane, uncombusted, is a potent greenhouse gas. So we've got the broad structure of natural gas, which is the cleanest and simplest, and you get to more complexity, which typical coal beds have half the periodic table in them, and the coal ash that comes from burning coal can have high concentrations in pretty toxic material. And we're going to talk about coal ash in a few minutes, because where do we put the coal ash? Sadly, in unlined landfills, because the coal lobby in the United States has been so powerful, and that coal ash then gets exposed to rainwater and things like that and leaks and contaminates water systems, where typically not in wealthy neighborhoods, but in neighborhoods of lower socioeconomic status. So just getting a sense of what comes out of the crock pot. And besides oil, gas, and coal, we wanted to save space to at least mark the fact that the other thing that we get is natural gas liquids that occur naturally. And so when I give the natural gas lecture, I'll elaborate more on this, because it's very common for NGLs, as we call them, to occur with natural gas. Natural gas can occur somewhere between a third and a quarter of the time with oil, but usually gas occurs by itself more often than not. But sometimes it occurs with these natural gas liquids that you see the composition on the left and the use of NGLs on the right. If someone said, if you were on a game show and said, what's the most common use of NGLs? The word I would throw out is plastics. We use NGLs for many other things, for antifreeze, for barbecues, for home heating, so propane, things like that many of you have heard of. But hydrocarbon gas liquids or natural gas liquids are they're not as complex as petroleum or crude oil. And they're much more liquid than natural gas. So they're in this space in between. And the detail on this slide, which all of you have, elaborates on the different uses of the different natural gas liquids. It's very, when we're taking oil in the upstream and we produce it out of the ground, the midstream is refining oil, largely into gasoline and jet fuel, but then a whole bunch of other products. When we produce natural gas out of the ground, very often before the gas can go in the pipeline, we have to have a natural gas processing plant. And that natural gas processing plant will extract the natural gas liquids and sell those off to market for those valuable products that industrial users largely and some consumer users appreciate. So this is switching back to the geologic side of things. Most of you at some point, whether it was in elementary or middle or high school, got exposed to the geologic history and the idea that the Earth is somewhere in excess of 4 billion years old. So we have Precambrian rocks, et cetera. What this is meant as our oldest rocks, which some of you get to see like on the Canadian Shield and other places like that. The goal of this is to show you where most oil and most gas and most coal occurs by age if we were to date it geologically. And there's a couple key ideas that are important to why here and why now. So ultimately, to get big accumulations of coal, for instance, you need periods in geologic history that were very lush in plant life, very lush. So that when a big climatic event took place that caused those to get captured, and that organic material to get captured, it was because there was this very lush resource that was captured in that period of time. There's a lot of carbon dating work we can do. There's a lot of fossils that we can use to identify what was going on when. But generally, we can tie the biggest accumulations of fossil fuels to periods of very prolific biological growth, coal-wise, woody, peaty planting material. And by the way, most natural gas is tied to a coal origin rather than an oil origin. I'm going to go back to that for a minute. Excuse me for jumping around. So there are multiple ways that we can get natural gas. We can get natural gas by overcooking petroleum molecules, crude oil molecules, which are very complex. So petroleum, those are very simple petroleum molecules. They can be much more complicated. And the easiest thing to break off of them, if they get more pressure and temperature than you need to form crude oil, is to break off the natural gas off them. So that is associated natural gas, right? But coal is, look at that, how complex that is. And most natural gas actually can be tied to being produced out of woody, peaty, planty, coal-like sources, but at great depth. And one of our greenhouse gas emission problems is actually coal, well, and actually worker issues, is active coal mines have methane leaking out of the coal and that are very vulnerable to fires. So sometimes you've read about coal mine fires which affect workers. But we also have a lot of methane leakage just naturally happening out of abandoned coal mines or active coal mines. And because methane in the first 20 years or so is 80 to 100 times more potent than carbon dioxide is, we really need to be managing methane emissions in a much more aggressive way than we have in the past. So we can have other processes that result in natural gas. We can have natural gas that comes out of a landfill. We can have natural gas that comes from permafrost. So natural gas origin has a multitude of sources, whereas oil and coal are much more specific. Where do the fossil fuels occur? So if you take the Earth and you shrink it down to the size of a basketball, the Earth's crust is as thin as that balloon. Everything inside that, if it were the Earth, is molten, okay, and super hot. So the oil, the gas, the coal is all coming. Most coal that we mine is no deeper than 3,000 feet. Most oil and gas that we drill for is less than 15,000 feet, and the average depth is 8,000 or 9,000 feet, okay? And an important part about thinking about this, if everything inside it is molten, the way to think about the Earth's crust, it's like a big scab. And it's broken, it's brittle, and it's moving around slowly but surely over time. It's important to think about the fact that the way we see the Earth today and the way we find resources, whether it's lithium or oil or gas or coal, it was different. So see over on the right-hand side, so there's Pangaea breaking up into the world we see today. And so the oil and gas and coal deposits were created tens to hundreds of millions of years ago. And for the people who historically up until now have explored for these resources, you have to actually imagine what was the world like then for oil and gas and coal to be deposited in these rocks. That's what geologists do. There's a lot of Sherlock Holmes of imagining what was the environment that these things were discovered in. And so the movement of plates over time and the constellation of where everything is today, that's just the way things are today. 100 million years ago, it was very different. And we saw in that geologic table that a lot of the organic material actually came from 200 or 300 million years ago. And so if you're an exploration geologist for lithium, for cobalt, for oil, gas, coal, et cetera, you have to take all this into account. So now we're going to talk about some nomenclature that when you read the newspaper or you read reports of things, we hope will be helpful. In your assignment, you had an article from the EIA that showed an oval. And it showed how to think about resources and reserves. So the Energy Information Agency, which is part of the Department of Energy, they use the oval. The US Geological Survey, which is part of the Department of the Interior, they use the McKelvey diagram. I'm exposing you to both. It's the words and the concepts that matter, whether you use an oval or a rectangle. So when we're talking about any stock resource, which is coal, oil, gas, gold, silver, lithium, something that occurs in the earth that we mine or extract out and is not renewable, that it has a resource, okay? And so the resource is the best estimate of every molecule that the best mines in the world or the best mines in Montana or the best whatever geospatial area we pick, we gather the smartest people and they come up with their best estimate of what is there regardless of price or technology. How much of it do we have? Whether we can actually get to it or not. Okay, so that's the resource base, and this is the framework for thinking about it. So then you impose on that, well, what's technically feasible today? So that's the technically recoverable resources. That doesn't mean, so that's the best estimate of what our tech can do, kind of regardless of price. So the reserves are what's economically, technically recoverable, okay, with today's prices. But the proved reserves, you have to have drilled a well and found it. You have to have dug a mine and found it to get it to be proved. In the SEC, the Securities and Exchange Commission, if you're a resource extraction company of any kind, you have to get a third-party independent audit and review of what are your proved reserves of oil or gas or coal or gold or silver or lithium or whatever. So if you end up working in the finance world and understanding this, it's important to understand the difference between the resource base, which is how much is there, and what's proved. And it turns out when we look at all oil and gas wells and fields all over the world, we're lucky if we can get 20 to 25% of what we know is in the ground there out of the ground, because the molecules stick inside the rock. And in a few minutes, we're going to look to see what the reservoir rock looks like, and you'll go, oh my gosh, how do they get anything out of this rock? And with coal, we can't just like rip the whole coal bed out. We have to leave pillars of coal in the ground to keep it from collapsing in some cases. And so what's the recovery factor from a resource ends up being part of the proved reserves calculation. You may have a lot more there, and you can see it, and you can measure it, but you can't extract it. So understanding that, and that financial markets work off proved reserves. So if the price of, we'll stick to oil, if the price of oil doubled, what would happen to your proved reserves? Okay. If you had a revolution, much like we had with angioplasty, where when I was growing up, if you had a clogged artery in your heart, it had to be open heart surgery. And now we can do horizontal drilling through your leg up to your heart and do angioplasty, take out the plaque, and you're all done. So we basically did the same thing in oil and gas as we figured out how to drill horizontally. In a vertical well, we're only penetrating 100 feet of a reservoir, and now we can penetrate a mile of a reservoir. What do you think that does to proved reserves? Up, way up, okay? So that's why this framework's important, and I don't care whether you use the oval or the rectangle, but I want you to understand the broad idea. So reserve to production ratio is meant to give planners and resource folks a sense of how much have we got. Okay, so if we have these proved reserves at current rates of production, how long will that last us? And so that's something people keep track of. And the truth is, so this is just showing it for oil, gas, coal, and uranium globally, and it shows you we're not running out of fossil fuels. Something I told you in the very beginning, something I think you knew. And so that's why peak oil or peak gas or peak coal is going to be driven by demand, not by supply. We have plenty of this stuff. We keep finding it. We have better tools to find it than we had before. So this is meant to highlight and give you a sense, because it's like, where does this occur? Where are the proved reserves? So ironically, the US, largest producer and consumer of oil, and we only have 4% of the world's proved reserves. So how do we pull that off? Well, we have a democratic society. We have private ownership of mineral rights, which no other country in the world has. The governments control the mineral rights in the subsurface, so it's less entrepreneurial. We have a lot of innovation in terms of how our markets work compared to other countries. So, and this shows you where in the US, where are our proved reserves, with Texas being number one by a long margin. In the Permian Basin, we'll talk about more, is super important. Here's where the gas is. So 3 countries dominate proved reserves of natural gas. The United States is not one of them. And again, Texas is the most important state in the US for natural gas proved reserves as well. Pennsylvania went from nothing to a lot because of something called the Marcellus Shale, which only became economic with horizontal drilling, and it became very economic. And here's coal, showing you that where those reserves are, and then showing you in the United States that if we had done this for coal in the US 30 years ago, there wouldn't be much in the West, but actually the Clean Air Act came in and said, actually we put a huge premium or regulatory requirement on low sulfur coal, and that migrated our coal, domestic coal mining, from Appalachia basically to Montana and Wyoming, which have much lower sulfur coal. So now we're going to talk about the environment a little bit. This is from your Fast Facts, which everybody downloaded off your assigned readings. Basically, part of the reason I think you're taking this class, I hope, is the appreciation, the fact that fossil fuels, all that chemical energy, all that biomass is full of carbon. And we are very inefficiently delivering all kinds of energy services with a very high carbon footprint. So this is a list of impacts at the top. Big climate, we make this distinction between strictly focusing on the climate impact, but other environmental impacts. This shows the rise of greenhouse gas emissions globally just over the last 20 years, and which resources are contributing to that. And this shows in the United States, the role of what are the greenhouse gases, coming from fossil fuels, from energy production, and their role. And one of the things that this is fine data, but it doesn't give you the duration of these gases in the atmosphere. And that's something we'll circle back to when we have our natural gas lecture. So I think everybody in this room knows that fossil fuels are our primary source of greenhouse gases in the atmosphere. So this is the part where I have my next thing, which is, as someone who's 39 going on 64, I'm very aware. I have 3 daughters who are 30, 26, and 21. And I'm very aware, I'm going to throw this, so be careful just to keep everybody awake, that we have created a lot of poop. So, and that legacy of fossil fuel infrastructure, so you were great to tie me in bringing up the idea of refineries. So you see, so this is kind of a head count of what have we got out there. And one of the things that's really tricky is we actually have to be obsessively focused on climate change and greenhouse gases and things like that, but we actually have to worry about these things too. And in some ways, kind of a tricky issue is while we're focused on climate, it's easy to not be paying attention to some of these other issues. A really interesting thing that's come up around coal ash is, remember I talked, so it's been very poorly regulated. It has a lot of the periodic table in it. And there's actually recently been a renaissance of people saying, let's go excavate those landfills and mine the coal ash for EV metals. Because that's the variety of things that are in that coal ash, which was just considered waste. And so now there's an economic incentive to say, can we go in, harvest that ash, reclaim that? And there's a market incentive that before EVs didn't exist. So ultimately, the government is trying to get engaged in some of these problems. There is, as it shows, the bipartisan infrastructure law created incentives to address orphaned wells and also to focus on mine reclamation, but the amount of money is trivial relative to the scope of the challenge. So 25 abandoned oil refineries, big cleanup issues associated. Has anybody ever heard of the word catalyst when you think of splitting crude oil into all its little pieces? So those catalysts and the spent materials for those are actually, in many cases, toxic. And some of our refineries in our country are very old, and we didn't have the EPA during the early period of oil refining. And so there are a lot of Superfund sites that are old refineries that are just kind of stuck there, and they become the property of our country, right? Because the owners of those refineries don't even exist anymore. Same thing with our abandoned wells. When we say they're orphaned or abandoned, it means the companies that drilled them don't even exist anymore. So how do we deal with those issues? So there's much more discussion about this slide today than there was 5 years ago. So I'm excited about the progress. And it's a challenge because we're dealing with multiple challenges at once. How do we decarbonize and how do we clean up? And that's why I highlighted this idea of the legacy issues, which generationally are not fair to you all, but they're part of the reality of what we need to address going forward. This just came out in August from the International Monetary Fund, and they have this report where they highlight explicit subsidies, which is we're going to provide a tax incentive for oil. And then there's implicit subsidies, which are the obvious things we should be putting a price on that we're not, like the value of the carbon associated with it. So this is just showing globally, the trillions of dollars of implicit and explicit and how those have been rising. And then they detailed it here, and what really caught my eye was the last sentence here saying, the IMF is saying if we eliminated these, we'd prevent 1.6 million premature deaths, we could raise government revenues, and we could get emissions on track. And so this goes back to how do we price externalities? So hopefully all of you, whatever you're studying at Stanford, you'll take an econ class and learn more about the supply and demand curves, if you haven't been exposed to it already, of thinking about these externalities, and we won't get where we want to go until we figure out how to price those things. So this is our introduction, a tour to thinking about when we think of fossil fuels, what do we mean? Where do they come from? What do they have in common? How do we describe them? I think with that, I'm going to give it a wrap.